Good evening. Today we'll start the class now. I will start with the continuation of that one problem that we were not able to solve, that 3D and 5D, and why we are not able to solve by this simple method. That I will tell you. Then we'll continue the class. Okay. Okay. First of all, so in that 3 day and 5 day BOD problem, they have done third day and fifth day BOD, and we have to calculate K, rate constant KD. But what we got in that equation is it's around. I'm just this coefficient I'm just putting. So I think it's around 1.5 e raised to minus 3 KD minus e raised to minus 5 KD minus zero point 0.5. Now, don't mind these things. Only think that these two things equal to 0. So this equation, we have seen this minus 3 and minus 5 kd. So we already solved one equation which is with minus 4 kd, some plus or minus e raised to minus 2 kd, plus or minus some value. For example, so anybody try to solve this thing? So actually this equation is in the linear form, so we can't solve in the normal way that we have solved here, putting like x equal to one value and x square is another value. This method is not possible. Also, you can't take the log also, like that log you can't take. You can take, but again the equation become very tedious. The thing is, you have to use some numerical method to solve this. For example, you can use Newton-Raphson method to solve this. So we can't solve in the normal way. Okay. So normally, the if I told you, the this should be, one should be x, another should be x square. So if e raised to minus 2 kd, then another is e raised to minus 4, e raised to minus 3, then we have to, when we square it will become e raised to minus 6. So like this we can solve this way. Otherwise you have to use the numerical method, Newton-Raphson method, or if you have MATLAB, then you can put the equation and find the kd value. Okay. So next we will start this COD measurement. How in the lab COD is measured. So COD means it's chemical oxygen demand. So first of all, starting, this is the main plot for the COD measurement. Then here we are first hopefully like the screen is visible for you, and the letters are little small, but I think if you download this slides, or if I hope you people are seeing in the laptop, so that this is more visible. So here we are taking, you have to take distilled water and your sample, the sample that you have to measure the COD. That is, you have collected some wastewater, then you have to measure the COD. So for that, you have to take that water, and there should be distilled water also for the comparison. So here, before starting, you have to wash the tubes with the H2SO4 to prevent the contamination, and then ideally you have to take around 2.5 milliliter uh, of the water samples into see, two tubes. Then what you have to do is, now add 1.5 milliliter of potassium dichromate to the both tubes. Okay, first you have 2.5 milliliter of distilled water and other wastewater. Then in the same this tubes, you have to add the potassium dichromate in the both samples, distilled water, and this is your wastewater, for example. 1.5 milliliter to both. Then what you have to do is, you have to carefully add around 3.5 milliliter of the sulfuric acid reagent to the both bottles. And here, what you have to, so here see, you have to add the sulfuric acid reagent down inside of the vessel. So an acid layer is formed under the same digestion solution layer and tightly cap the tubes. So this one, after adding the sulfuric acid, you tied the tubes properly. Then what you have to do it, you have to transfer these two tubes into tightly closed tubes. Then you have to keep in the COD digesters at 150 degrees Celsius for 2 hours. So at this time, your this oxygen is used for by the chemicals. Then what you have to do is, you have to take out the samples after 2 hours. So this time the chemicals will use the oxygen inside the sample. Then after 2 hours, you take out both tubes, and then you have to cool at the room temperature. So you have to keep it for some time, make it cool as the room temperature. Then what you have to do is, then you have to take a burette. You have the solution here, and then in the burette with freshly prepared ferrous ammonium sulfate, FAS. So then you are adding the FAS to this both samples separately. Then what you have to see is, first you are add 2 drops of ferrous indicator. Then when you add at what what volume of this ferrous, when you add, you have to measure the at what volume you are adding, how much volume you are adding to the solution. Then what you have to do is, you have to see at what volume this changes to the this color. So the initially it is mentioned here, the color has to change from blue green to reddish brown. So when this color changes, and at what volume you are applying FAS, at that particular volume this color is changing to the reddish brown. That oleum you have you are measuring. So that oleum you have to measure for the blank, that is, you have to measure for the distilled water. Also you have to measure for your sample. So then you should know the molarity of FAS. Then you have to put in this equation to calculate the COD. So A minus B, A for the distilled water, how much, at what volume of FAS you got this change in color. Then minus B is the volume of, at what volume that you applied FAS to change the color to reddish brown. So you measure the volume at this per two situations, for the DI water and for your sample. Then multiply with the molarity of FAS. Then 8,000 divided by volume of the sample, the volume of the sample that you have taken. So this is the way how you have to calculate the COD. Okay, got it? Okay, okay. Now clear na? Okay, now we'll go for the, yes. So DO measurement. So DO measurement means we have to further, we have to go for the BOD. First, this is the DO measurement instrument. So here you can see this is the instrument, and here the screen easily it will show once you dip the electrode to the sample, it will measure the DO. Then we will get to know how much dissolved oxygen is present. So, but how you calculate BOD? That is our main question. How do you do BOD calculation? For that, I have just taken this question. see the question. So when we analyze the question, you'll come to know how BOD calculation is done. So here, this question, a 50 milliliter of water sample is, so for the BOD, normally, um, we have to dilute, because when we take more concentrated wastewater, that we have to dilute it for the convenience. First of all, see, 150 milliliter of water sample is diluted to 300 milliliter a nutrient solution and incubated in dark for 5 days at 20 degrees Celsius. And initial dissolved oxygen concentration is around 9. So initial dissolved oxygen concentration is around 9.05 milligram per liter, and the final concentration is 4.25 milligram per liter. The blank for the dilution water decreased in dissolved oxygen concentration from 9.05 milligram per liter to. Okay, the from 9.05 milligram per liter to 8.8 milligram per liter. So normally the BOD is estimated as for the 5 days. So how you are, like you calculating this? We should need a blank one, that is like distilled water we have to take. That is our the benchmark, or we have to compare. Then we have to calculate the oxygen decrease in the sample. These two things is we need. This is distilled water, and this is our sample, like what we have done for the COD also. We were doing for the comparison, we are taking DI water and DI water also. So what you have to do first is, uh, you have to collect the sample. Then you have to, so this is your wastewater. Then if you take the wastewater here, but if your solution is more concentrated, for example, uh, your sample is more concentrated, very concentrated in the sense your wastewater is so much very much, tedious is there. So then what you have to do, you have to dilute. So for that, what you have to do is, you have to take the wastewater, and then uh, you have to dilute it to make our measurement within the range. So first of all, I am start okay starting with the this one. So first of all, you take the wastewater. Then what you have to do is, you store in the BOD bottles. So why we have to use do the means collect in the BOD bottles is, specifically this is made for the measurement of BOD, and it will be tight so that more oxygen can not enter into the sample. It will be airtight, so that we'll get to know our BOD in an accurate manner. So if the sample has high organic load, then dilute it with O2 saturated distilled water. So if your solution is so much concentrated, then what you have to do is, you have to take DI water. So then you have to take DI water, but you should make sure that your DI water is saturated with O2. So how do you saturate your DI water? You have to aerate this DI water, and make sure that DI water is completely saturated. Then there is no further oxygen is able to dissolve in the water. Then this saturated water, DI water, you have to pour in your sample to make it dilute. Okay, because that should be, the measurement should be in our range of calculation. For that only we are doing that. Then what you are doing is, then this you are taking this is our final, after aeration, we have enclosed sample here. Then in that, what you have to do is, you have to give some nutrients. you have to provide some nutrients. So for example you can give phosphate, then magnesium sulfate, calcium chloride, or yeah, these type of things you can give. And then uh, what you are doing is you are providing some situation, a possible condition for the microbial growth. Then what you are doing the next step is incubation. What you are doing in the incubation, you are actually growing bacteria inside the sample. Then after 5 days, after 5 days you are measuring the dissolved oxygen content. What How much dissolved oxygen is there. So you measure the dissolved oxygen at the final day. That means it is the fifth day you are measuring. So 5 day, 3 days there, 5 days there, but 5 days more standardized. So for the 5 days, you have closed your tubes and keep it in the incubator for the 5 days to the let the microbes utilize the oxygen. Then you measure after the after this days, then you take the sample out, then you are measuring the dissolved oxygen. Okay. Then what you have to do is your BOD 5 is equal to, that means BOD at initial, then sorry, this not BOD, dissolved oxygen initial, then dissolved oxygen final, then this is divided by total volume of dilution that you have taken. Sorry, yeah, total volume of dilution you are taken into volume of the sample. So this particular thing you can take like dilution factor. So here you can see that this is the dilution factor they have taken. So that is, first of all, 300 milliliter is the volume of the sample. Here see, this volume is diluted to 300 milliliter. So this is the volume of the sample, and this 15 milliliter is the water sample. So here total volume means this total volume of the, why they have taken, okay, don't this one, see here, this is 300 milliliter by 15 milliliter. So here 300 milliliter is the here you see that 15 milliliter is the water sample. Here water sample is the 15 milliliter, and it is diluted to 300 milliliter. So this is after dilution, it will become 300 milliliter. So you have to divide this after dilution, this is the totally how much it become, then it should be divided by 15, that is the initial water sample volume. Then you get the dilution factor. Then here you see that initially BOD 5 you will get here, that means 4.80. So here you can see somewhere, yes. So decrease in the oxygen, okay, decrease oxygen decrease in the sample minus okay. So in this in this calculation, they have actually taken the both sample, distilled and the other. So there should be, there is a slight difference for that. See here, they have taken first one is 4.80 is the oxygen decrease in the sample after the fifth day, and 0.25 they have taken oxygen decrease in the blank. So you can do this way also, and you can do this way also, like you are measuring DO at the initial time, you are measuring DO, and you are making it diluted, then you are converting into for 5 day you provide for the microbial for the growth, then you measure the do at final, then you are minus this with the dilution factor. So here in this case, okay, in this case what is dilution factor is the volume of sample divided by total volume of dilution, which I have mentioned here. So here what they have doing is they are taking two, so oxygen and decrease in the blank, also your that sample also they are taking, and they are measuring the decrease in the oxygen at both samples. Then they are taking BOD comparing this two solutions. Got it? Blank is the DI. So DI is the blank. Then you are providing in the DI water also, you are providing, nutrient. And then you are seeing that how much after providing the nutrient, then also you are putting in the incubator for the incubator, and you are providing what you are providing the situation for the microbes to grow, and for the in the DI water, and then you are seeing the how much oxygen is decreased. And here in our sample already there are a lot of a lot of nutrients compared to the DI water, and then you are seeing how much oxygen is consumed at this particular sample, then you are comparing the both sample to get the BOD5 for this particular question. Sorry. So here for the DI water, for the dilution of the sample that you are taking, for the sample you are taking, for you want to for the dilution you have to take the saturated DI water. So you have to make the, so you have to see only, yes, you should not for your sample there should not be any influence of uh, if the DI water is less saturated, there is a possibility that from the air also there there is more oxygen can come inside. To resist that, we are saturating the DI water to dilute. Okay. Okay, so next is the alkalinity. So alkalinity is also, it is some same like what we have done in the first. Um, we are using different chemicals, but we are using titration only to find the alkalinity of the sample. So you are taking, first of all you are taking the burette, and you are cleaning it with sulfuric acid, and that is the initial step. Then what you have to do is you have the water sample here. So you are taking the water sample, then you are filling the burette with zero point zero 0.02 sulfuric acid and adjust it to 0, then fix the burette in stand. Then what you are doing is um, using a measuring cylinder exactly 100 milliliter of sample and pour it into 250 milliliter of conical flask. So this is the conical flask. Then you are taking 100 milliliter of water sample, then you are putting in the conical flask. Then what you are doing, you are adding a few drops of, so now what you are doing, you are so from this diagram I'll explain. So here you have the this is the, see, this is the conical flask. So here you have already, you have the your sample, then you should add 2 drops of phenolphthalein indicator. So you added the some few drops of phenolphthalein indicator, then the color of the solution will turn into pink as you seen in the figure, pink. So then what you have to see is you have to see when the color changes due to alkalinity of hydroxyl ions in the water. water sample. For that, what you have to take is you have to take a sulfuric acid. So that is also, see here, zero point zero 0.02, you have to dilute to it sulfuric acid. Then you have to titrate the contents. So then you are just putting drop by drop the sulfuric acid. Then what you have doing is you have to find, see at what point the color of the solution will turn. So this is, first of all, it is a pink color. So you are seeing this, and at what time this pink color disappears, you noted down the amount of sulfuric acid you poured down. So you measure the volume of the sulfuric acid, at what uh, volume the color of the your sample is changed colorless. Okay, so that volume you mention here. So the same solution you are taking, and then what you have to add is you have to add 2 drops of mixed indicator. Then this particular solution will turn to this blue color. Then again you have to continue with the titration with the sulfuric acid, that is also this diluted sulfuric acid. Then you see at what time, what volume this color of solution, which is blue color, it will turn into red. So this oleum also you will mention. So you have to mention two oleums, at what time this particular our sample, uh, after adding phenolphthalein indicator, then at what particular oleum it will change to colorless. Then from after again you're doing the second titration in the same sample after adding second indicator. So then what you have to do is you have to find at what oleum this is changing into the red color. So these two oleums you are measuring. Then what you have to do is this one. So you calculate the total oleum. So you know that you have used the particular oleum of sulfuric acid here and here also. So here alkalinity as CO3, calcium carbonate is equal to, you calculate the total volume of the total volume of the acid into n into 50,000 divided by volume of the sample. So here you can see from the from here you have two types of um, see here you have two oleum 1 and this oleum 2. You have the total oleum here, and n is the normality of the acid that we are using here, using H2SO4. Then this 50,000 is the equivalent of CaCO3. Then volume of the sample that we are taking for the alkalinity measurement. So when you put these values, then you will get the alkalinity as CaCO3. Thus you can calculate the alkalinity. Got it? Sorry. So that I have to check mix indicator. I think this mix indicator will change the solution to CO3 and does HCO3 2 minus ions. But mix indicator, I thought. Okay. So you're doing lab in this? So this is the, yeah, yeah. No, no, this one, this one is the, this is also, this is an idealized one, because this one I have taken also the person who like suggested me by a person who doing this analysis. This like, so there will be a lot of method. I think you're following some other method like that, right? Sorry. Yeah, I do have. Yeah, I do have. Other than this phenolphthalein, you can use some other indicator. I think you can use different indicators at this 2 point, but you should know at what color it is form and what it changes when you add acid. Yes. Okay. So I hope like it can vary. Like different labs may do different indicators. That's what I'm. Okay. Okay. So then we go to our today questions. So first one. So if you want to know specifically what is mixed indicator, I will let you know next class, because I am now doing this type of experiment now. I am a membrane fabricator for the currently. So yeah, I will let you know the mixed indicator next time. Okay. Yeah. So now we'll go for the this week questions. Okay. Okay. So hopefully everyone has seen the lecture notes by for the fifth week. This is the fifth week, right? So have everyone have noted down the the portions? Okay, we'll start. First of all, first question: sedimentation is an example of four options are given: unit processes, unit operation, both A and B, neither A or B. A or B. What is the okay? Oh, someone else was okay. Unit operation. Why it is unit operation? Huh. Yes. 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 Right. Right. So now we go for the next question. I think it's small. Okay. So grid chambers are located. Four options are given. Before bar screens, after equalization tanks, after sedimentation tanks. D after bar screens and before primary sedimentation tanks. What is the answer? What is the answer? Anyone can comment? D. Yes, D is the right answer. After bar screens and before primary sedimentation tanks. So okay, okay. So what is the I will come to this. See this. So this is the grid chamber. Usually, you see here inlet and outlet, and why the grid chambers are using. Anyone can tell what is the usage of the grid chambers? Yeah, it will settle down here, and then we can separate. See here, it will come. So then it is mentioned. So it is actually after bar screens and before primary sedimentation tanks. So unit operation. Okay, this you can read once I upload the the slides in the drive. You can download and read. So here, third question: the retention period of grid chamber is in the order of. Okay, I will increase the size. Okay, the detention period of grid chambers is the order of which one? Anyone has idea? So here, see what is detention period or a retention time. So here, retention time of a grid chamber is typically in the order of 30 to 60 seconds. This is the period sufficient to allow heavier grid particle to settle out of the wastewater flow before it moves into the subsequent treatment stages. So it is the sufficient time it is needed to settle down the this grid particle. So normally the time the typical time range is 30 to 60 seconds. So that means here, when you say it is, this is the most appropriate answer, so it is 30 to 60 seconds is the time order. Okay. Next, here, for the detention time can vary depends on the three factors: design and size of the grid chamber, flow rate of the wastewater, and characteristic and concentration of the grid. Okay. Next, the equalization tank is used to, four options are given: eliminate variation in the flow rate, improve performance of the downstream process, balancing fluctuating concentration in the effluent, D, all the above. What is the answer? Here it comes for the equalization tanks, all this D. D will come actually, because all these things are, you know, done by the equalization tank. These all, uh, it need to be, have to do all these three things: eliminate variation in the flow rate, improve performance of the downstream process, and balance the fluctuating concentration in the effluent. These three has to be done by the equalization tank. So the correct answer is D, all the above. So here you can see this is the equalization tank, you can see. So see here, the impure water, this inflow is coming, and here you can see the sliding plates for the grids, for the equalizing the flow rate. Also here the pH adjuster is also there. And so in this particular equalization, things are mainly doing: it is balancing the flow, and then concentration stabilization, and then improving the these all. When we do this, if there is a more variation in the flow properties and the concentration, the efficiency of the whole system will be low. So for avoiding this, this equalization tank is mainly doing this flow balancing and concentration stabilization, to make the system more efficient. That's why here, it is eliminating the variation in the flow, improving the performance in the downstream process, and then it is balancing the fluctuating concentration in the influent. So it's all done by the equalization tank. So then, next question: removal of suspended organics and finer inorganics usually take place in which one? Removal of suspended organics and finer inorganics. Anyone can tell? Yes. Primary clarifier. Primary clarifier is the answer. Next is, what is the critical settling speed is, four options are given: equal to overflow rate, B, settling velocity at which all particles are removed irrespective of their size, C, maximum settling velocity of the particle, D, none of the above. So you have to say what is the critical settling speed is related to any of this options given. So here you can see, then you can comment on this, what is the what will be the option true for critical settling speed. So you know what is critical settling speed? That definition is given here. Critical settling speed is the minimum velocity at which particle will start to settle under the influence of gravity, assuming other factors like turbulence are minimized. If the turbulence are there, what happens? If the turbulence are there, the particle will be in the flow with the turbulence. It will not settle that much properly, uh, to the settle down to the down. So here, if the when the turbulence is minimized, it because of the gravity, the particle will settle down to the base, that is at minimum velocity at which this particle will settle down to the base is called the critical velocity. So what is the so how do you what option you select? Sorry. No, not settling. So overflow rate. Yes, overflow rate is the correct answer. Overflow rate is the correct answer. Okay. Now, seven question. Surface loading of a for a rectangular sedimentation tank with length L, width B, and height H having. Okay. Okay. Okay, surface loading for a rectangular sedimentation tank with a length L, width B, and height H, having design discharge of Q, and is represented by which of the following options will be suited to represent by these all parameters of a rectangular sedimentation tank: length, width, height, and then discharge Q. Which one? So the answer is B, that is Q discharge divided by B, it's the width, and then L is the length. I think if you guys have seen the lectures, you can easily answer these questions, I think. Okay. Next question. Here, the overflow rate of a sediment tank is four options are given, also called surface loading. Overflow rate is independent of depth of the tank, or C depends on length and width of the tank, and D is the all the above. So what is overflow of a sedimentation tank? So it is refers to the discharge of treated water from the tank, typically occurring at the top of the tank, and then proper management of overflow is crucial for ensuring the effective operation of a sedimentation tank and the overall efficiency of a wastewater treatment tank. So overflow of a sedimentation tank is the discharge of a treated water from the tank. Typically it is occurring on the top of the tank. How it is happening? So this there will be water particle, and this will settle down, and then this top water become over of, means they will uh, not contain that much particle, and this discharge will happen from the top of the tank. So what it is, overflow of a sedimentation tank is called surface loading, is independent of depth of the tank, depends on length and width of the tank, or the above. Which answer is right? So what is overflow rate, and then is also called surface loading, is independent of depth of the tank, depends on the length and width of the tank, all the above. Which one? D is the right answer. So here also we have the design, here you have seen discharge divided by this is width and this is length. So here see here, independent of depth of the tank, depth of the tank is not related to this overflow, and also this is called surface loading, and depends on length and width of the tank that we have shown from this particular relation. Okay. Now Ninth question, settling velocity is typically highest under uh, so different settling chambers are given. So in which settling velocity is typically higher? Discrete settling, Flocken settling, zone settling, compression settling. Which one? B is the right answer. Yes, yes. Flocculant settling. So here, see here, what is flocculant settling? In flocculant settling, the settling velocity of particle can be higher compared to the other settling regimes due to the formation of flocks aggregates in of fine particles that stick together. Flocks aggregates of the fine particles that stick together. Thus the weight of the total, that particle will high, then this will have higher settling speed compared to the other type of settling regimes. So here you see the increased particle size. Then also when it's settling, so it increase particle size, reduce drag force. What is drag force? You know, right? What is drag force? When it move down, there should be a force upward. That if we are also moving through air, if you are driving a car also, there is an opposite force that will react because of the shape of the vehicle. Also, that you know, right? This drag force, you know, right? So here the drag force will be less and improved settling efficiency and collective settling, reduced interparticle interaction. So here, because of this is large particle size, it will settle down quickly with higher velocity, with reduced drag force. It will come down compared to other type of settling. This flocculant settling is having higher settling velocity. Next, yes, sorry, yeah, yes. So this is compared on the basis of settling velocity. Like, huh? Yeah, but in yes. So here in zone settling, this individual particles, it will form a clumps. So the settling, so it here the particle form the name it is given like clumps or flocks. Then it will the when it's settling down, the speed is not by the it is decided by the total clumps that is formed, and it is not from the individual particles. So here I think so I sorry, so yeah, I think here, yes, here individual forces also apply, but here I think the interaction between this is not there, right? That is the difference, right? Anyone can comment on that interaction between particles in flocculant settling and zone settling? Okay. Yes, cohesive force means interactive interaction force between them, right? Cohesive force, right? Okay. Sankhamitra, you got that point? Okay. Yes, see, here it goes. Yes, in all these, just the settling velocity is considered. So here in the zone settling, as the other student has commented, the cohesive force is acting. What is cohesive force? Cohesive force is the attractive force between the same type of molecules. Here the particles are there, and it has more cohesive means they are more attracted towards each other, and here it thus because of this force, it's the settling velocity is reduced. That's what I have understood. In compression settling, that I have to see, but the answer is this one. But can you repeat that? Okay, so in the bottom it get compressed, how it affects the settling velocity? Okay, that is due to this compressive force. Yes. See, in flocculant, it is mentioned the interact it become clump, flocculant, but it doesn't have the interactive force between each other. That force will be less for the flocculant. That's why it will move faster with higher velocity to the settling chamber. Okay. Okay, then otherwise this particular, you have seen the lectures for this particular thing. There is otherwise, okay, I will come with some diagrams for the next class for this four. Okay, next class I will go come with the diagrams. Okay. Okay. So the 10th question, which of the following is the tertiary treatment process in water treatment? So four options are given: removal of heavy metals, removal of high TDS, removal of nutrients, all the above. Which one is for the tertiary treatment process? What is the tertiary treatment process here? All the above, yes, that is right. All the above is the tertiary treatment, or removing of the heavy metals, removing of TDS, and removal of other nutrients. These all comes under tertiary treatment process. Okay. Now we'll go for the uh, okay. Now we go for the next question. So the tube and plat settlers compared with the conventional sedimentation tank generally require. So if we are going for the tube and plate settlers compared to the conventional sedimentation tank, generally require, the four options are given: lesser area, higher input energy, lower maintenance; then more area but lower input energy and higher maintenance; more area and higher input energy, lower maintenance. So what will be the answer for that? So, what do you think that for the tube and plate settlers compared to the conventional sedimentation tank, like what is the most suitable options here? Huh. lesser area, lower input energy, and higher maintenance. So here we will see here. So this is the conventional one, conventional. So here this is the, you can see. Okay, so now you see this. So here you can see that the settling, they have to, for it has to travel this much distance. So here the aim of the modification of the whole system is you have to decrease the mean path length you have to decrease for increasing the efficiency of the settling. You have to decrease the mean path length. So for that, what it is done normally, this particles are moving like this. You can make move like this, like see, started from here, here it is moving like this, or this particular platform, you can make like a angle, so like that you can do. So like that it is, they are varying the angles, then understanding mean path, how much path this particles has to travel, and what will be the efficiency for all these angles to achieve a good efficiency for the whole system. So when we do, see here, this is the, particles, it will travel and it will, come like this. So this way, compared to this particular setup, this particular way, you are decreasing the, a traveled, your travel path, and you're collecting the particles. That is the main main thing, for the improvement of this chamber. So here, what is this? Anyone can tell what is this and this? What is this one? What type of, here I told tube and plate settlers. So these two are tube and plate settlers. Which one is tube and which one is plate? Anyone can tell? Yes, this is plate and this is tube. So you hear the tube. See here, you can see this is in a rectangular tubes, and then we are, this is the inside, and the, this is collecting, the grids are removing from this particular uh, you know uh, place. Okay, any doubt in this? Anything? Okay, this thing I will talk in the next class with a diagram, and we'll go for the problems now. Can we start, or we'll need a 5 minutes break? 5 minutes break, then yes. Yes. Can we start? Can we start? Yes, okay. Here, question is determine the approximate detention time of a grid chamber with settling velocity 0.02 meter per second and depth is to width ratio is 1.5 is to 1 for treating a maximum waste flow rate of 10,000 meter cube per day and where flow through velocity is zero point 0.3 meter per second. So first of all, we can write what are the things it's given. So here first on the settling velocity, so vs settling velocity is 0.02 meter per second, and then here flow through the chamber, flow through velocity is zero point 0.3 meter per second, and then maximum wastewater flow q is equal to 10,000. Okay, 10,000 meter cube per day. So first you have to convert this value, convert this into meter cube per second. How do you convert 10,000 meter cube per day? So day means you have to convert into second, 24 hours, 60 minute and 60 seconds. You convert into meter cube per second. Okay, so q value you have, then they have given one more thing, depth is to width ratio. So depth is to width ratio is 1.5 is to 1. So you can write d by width equal to 1.5 divided by 1. So then d depth is equal to 1.5 width. So 1.5 width. So you have this all for information here. So your final aim is you have to find what is the detection time. So how do you calculate it? So now here this particular portion depth is to width it is given. So from this particular thing you can calculate the area. So the area you can write a is equal to width into depth area, and then this you can note like cross sectional area of the grid chamber. This is cross sectional area of the grid chamber. Then what you have to do is a is equal to width, you put w, d that you have here it is 1.5 w, which is a is equal to 1.5 width square. So area you have in this in terms of width. Then what you have to do is you have to calculate the length of the channel. So length of the channel, how do you calculate? Length is L. L is equal to depth into flow through velocity divided by settling velocity. So from here you calculate the length. So then you have, how do you calculate the retention time? That T is equal to length divided by VF. So this is the formula. So how do you calculate? So after this, you try length. I have given the formula d into vf by vs. So vf and vs we know. D, we don't know d. We know in terms of w only. Then what you have to do is you put this values here, and then here what you have to do. So after this, you have to you should know how to calculate d. So how do you calculate d? You have already, the area you have calculated here. So where is the area? So area you have here. Then you have to calculate area by means of, you have to calculate area in terms of q and vf, because here meter cube per second is there. So if you have divided with the flow rate, then m square, like this will get cancelled, then you get in meter square. That means area you can get from here. So area you can calculate, a is equal to q divided by vf. So you get cancel meter per seconds, and then you get in meter square area. So what you have to do is, this area you will put it in here. Then you calculate the value of w. What is w from this equation? Then you know the area. Then you can calculate here. From here you know what is the value of depth. Then what you have to do is you put this d value here in l. Then you know vf and vs. Then you calculate l. Then that l value you put it here in the formula for the detection time. So first calculate this one. So what is the value of q here after meter cube per second? In meter cube per second, what is the value? What is the value? Anyone know? This is 0.115 meter square, meter cube per second. Got it? In meter, I have converted the meter cube per day to meter cube per second. Got this answer? 0.115 meter cube per second. Got it? Yes. So then we can calculate A. Area is equal to flow rate. Here we know 0.115 divided by VF value also we know. VF is zero point 0.3. So area we get 0.115 divided by zero point 0.3. That is 0.385 meter square. 38 meter square. Any doubt in this? Anyone? So this particular area 0.38 you have to put here. So we know 0.38 equal to 1.5 w square. So from this equation we got what is width. Width is equal to, how do you calculate? 0.38 divided by 1.5. Then you have to take the square root. Then that means it will be, no, here it is given na, depth is to width is equal to 1.5 is to 1. Yeah. So what you are saying is length you should know, right? The question is given like this only. Huh. You can take this as well. So sorry. Yes. You okay? Okay, but this is solved question. Yes, answer is A only. Yes. So actually this is a solved question. Like I didn't understand your point. What you are telling? Huh? Okay. Okay. Yes, that is the here it is cross sectional area. So that means they have give. You can take like it is this one, this is one, and this is depth. So the cross sectional area you're taking, when you take this, you can take this also. What you're mentioning, this is one, and this one, or this is 1.5 you can take. So at all the cross section it is like 1.5 into 1, right? The cross sectional area. Huh. So that way you can do. Yes. So then here what you do, you get the W here, width you get. So width is, so D is equal to 1.5 into width what you are getting is point 0.5, point 0.5, which is depth is what, how much depth? 76, depth is 0.76. Then what you have, you put here 0.76 into. Yes, yes, yes. Huh. You can put like BF is cancel. Yes, yes. Yeah, 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 yeah. That way also you can do. T is equal to L means D VF by VS, and then VF will cancel and D by VS you can do, and you will get the answer. Yes, yes. So the answer is, yeah, 38. Yes, yes, yes. 38 you can put. That is the answer. Got it? Got it now? Okay. Then we go for the next question. So next question here, determine the, so we are taking the values which we calculated in the previous question to solve this question. So determine, no, okay, this is not okay. So here we are not taking the previous, this is a new fresh question. Determine the appropriate detention time of a grid chamber with a settling velocity of, okay, this is the same question we have. Yeah, no, third, okay, this is the next question. So for problem 16, number 16, determine the, oh, don't consider this one. So take for the previous problem that we have solved, determine the length of the grid chamber. Length, what is the length for a flow velocity? So here BF is given like zero point 0.3 meter per second. We have to calculate length. So in the here the Vs it's already given. Vs, where is the settling velocity, is 0.02 meter per second. So Vs is equal to point zero 0.02 meter per second. So we have to calculate L. L is the length of the grid channel. L is equal to D into Vf by Vs. So D we have calculated in the previous problem. Vf, it is given here. then Vs. So what is the answer for L? So D we have calculated here. D value is given. Where is D value? D value is 0.76. 0.76. Sorry. Yes, B is the right answer. Everyone got VF is equal to zero point 0.3 divided by Vs equal to 0.02. So you get the answer. This B. Option B is the right answer. Got it now? Okay, this is simple. Then everyone got it, I hope. Okay, we'll go for the next question. Next is so here the terminal velocity of zero point zero 0.01 millimeter diameter spherical particle with specific gravity 2.65 in water density of 998.2 kg per meter cube and dynamic viscosity of 1.002 into 10 to the power minus 3 Newton second per meter square would be. So we have to calculate what is the terminal settling velocity. So this is, we have to calculate the terminal settling velocity. So the terminal settling velocity is equal to Vs. Terminal settling velocity is equal to 2 by 9 into density of the particle minus density of the fluid divided by, okay, into gravity into r square radius divided by dynamic viscosity. Dynamic viscosity. So we have to calculate the Vs. So here you can put uh, what are the things it's given. So this is the diameter. So you can, here you can write D is equal to zero point zero 0.01 millimeter diameter. So you can convert into meter. So it is zero point zero 0.01 into 10 to the power minus 3 meter. Then you can calculate R radius equal to um, 0.005 into 10 to the power 3 meter. So this is the radius that you have calculated. Then what else you know? You know the specific gravity. So this specific gravity, you know that G is equal to G is equal to specific gravity G is equal to 2.65. Okay, this one. Then water density, density of the fluid. Water means it's fluid. It is equal to this one, density 998.2 kg per meter cube. Then what are other things given? Then yes, dynamic viscosity is given. Mu is equal to 1.002 into 10 to the power minus 3 Newton second per meter square. This all given. Then how do you calculate? What are the things? It's this, you know, dynamic viscosity, specific gravity, radius, you know, density of the fluid also, you know. What else you don't know? You don't know this density of the particle. So how do you calculate density of the particle? So that is equal to what is the formula? Specific gravity into density of the water. So then you will calculate 2.65 into density of the water 998.2. Then you will get here density of the particle in kg per meter cube. Okay, so calculate this value and put this in the equation, then you can get the settling velocity. Calculate and tell me what is the settling velocity. Sorry, one more thing here. This is specific gravity. Specific gravity, yes. Okay, this is SG. So that we are calculating for this. So this is different. What is the value of G? Acceleration due to gravity. Wait, one. Yes. This. These two are different. This is specific gravity that we are used to calculate the density of the particle. Then this G is for acceleration due to gravity. Got it? What is the answer? Just put these values. Density of particle we have calculated here. 2645 2645.23 kg per meter cube. Yes, yes. B is the right answer. So you get like this, right? I think it's like 8.9 into 10 to the power minus 5. Right? This is the right. This way you get right. Then that will be in meter per second. You have to convert into centimeter per second for to find the options here. Then how do you do? Just multiply with 100. Then you get this answer. Any doubt? Sorry, sorry, I didn't hear which one. I didn't. I can't hear some. Like I think some network problem is there. Can you repeat once more? Hello. Which one? Huh. Terminal settling velocity. Where is? Yeah. Terminal settling velocity only we have calculated. Yes, yes. No. What is the fine? This is the one you are getting right when you do this calculation. 8.9 into 10 to the power minus 5. You get in meter per second, then you convert into centimeter. So you multiply with 100. So do you do like do once more this calculation 2 by 9? Then you tell me the final value, like without converting centimeter per second, tell me the answer in meter per second. I think who has calculated first? Can you tell? Yes. Huh? Okay. Sorry. Yes, yes. Diameter is this one, and then you square, right? Yeah, yeah. The same only you are doing. I am also doing the same only. Yes, yes. I am also doing the same only. You do this, and then you get, you are multiplying with the whole. Then this is the answer you are getting, right? Yes. So then after this, you just multiply with 100. Then you convert into centimeter per second. That's all. Got it? Yes. Got it. So here see Vs is equal to 2 by 9 into 2, where's this one, right? 2645.23 minus 998.2 into 9.81 into, then you have this one r, point double zero five into 10 to the power minus 3 the whole square, divided by 1.002, this one, into 10 to the power minus 3. You solve this equation, you will get around 8.9 into 10 to the power minus 5 meter per second. Then multiply with 100, then you get uh, this one, 8.9 into 10 to the power minus 3. Then you write it like 0.0089 centimeter per second, this way. Got it? Yes. Okay, now we go for the next question. So next question, what is the head loss through a bar rack with an approach velocity of zero point 0.6 meter per second, and velocity through the screen is zero point 0.9 meter per second. So we have to calculate the head loss through a bar rack. So here, you know what is the head loss here. So two values are given. One is the approach velocity, and another is the velocity through the screen. So this one, how do you calculate? So this equation is head loss is equal to v1 va square approach velocity minus v approach velocity is this, and v screen velocity is square, divided by 2g. Then normally you can calculate this way also if it's more accurate, 1 by c. So this is like c value, c equal to 0.74 clean bar rack, and c equal to 0.64 clogged. So you calculate in two ways. You calculate if the clean bar rack, and second you calculate with the clogged also. So calculate, and we get two answer, then we'll match with which of the option given below, and we write that. So here va is the approach velocity, va is equal to zero point 0.6 meter per second, and then vs is equal to 0.94 meter per second, and g is equal to acceleration due to gravity, because that is 9.81 meter square per second. Then c value, you calculate the head loss at this two situation, if the bar rack is clean or if the bar rack is clogged. So at these two situation, you calculate the value of head loss. So head loss at clean situation equal to what, and head loss at clogged, what? Calculate and tell me. 38 mm, with what you have calculated for 30 mm? Head loss, which c parameter you have used? Okay, okay. That way also you can use here. When we this equation you haven't used, right? Okay, okay, fine. This is the answer for this. At this two situation you can calculate through this way, and see, I will calculate at the clean bar. So if it's zero point 0.7, then I'm getting minus 0.3038 meter head loss. That's why this minus came. Then if it's clogged, then I may get 6 minus 0.44044 if it's clogged. So here you say this, convert this into millimeter, then you'll get this 38 millimeter, and here it is 44 millimeter. So here this answer is matching 38 millimeter, we can say, for this. So I think here they have considered the clean bar situation. So they haven't given here C. So here you can assume the clean bar rack. So but you should know this also, if they ask separately, if it's a clogged, then this you have to use this coefficient as zero point 0.6. Got it? Okay. Sangamitra? So I have done two times because when I have calculated without this parameter, this was not matching. So then when you do with this parameter, so then so this question they haven't done, clearly mentioned that whether this is clear bar rack or clogged one. So if in the question if it's not mentioning, you can do both, and if the options are given, you can match with the answer, or if this answer is not there, you can assume both situation. So you can write in the clean bar rack situation or in the clog situation. C value you can remember. The I think the other guy, what is your name? Yes. Okay. Okay. Clean bar situation. Okay. 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 Like that. Okay. Any other doubt? Can we go for the next question? Yes. Sangamitra, you are clear, right? Okay. So next question we go. Then here question is, the settling basin at a wastewater treatment plant having a flow rate of zero point 0.6 meter cube per second has an effective settling volume of 20-meter long, 3-meter tall, and 6-meter wide. What percentage of particles that have a settling velocity of 0.003 meter per second will be removed? Okay, so what you have to calculate at how much percentage of particles at this particular condition removing. So they are given four options: 100, 80, 70, 60. So from here you have to calculate the removal percentage of the particle. So for this one, so here this um, Okay, so for this, what you have to do is, first of all, you have to calculate the surface overflow rate. SOR, surface overflow rate. So that is equal to discharge divided by surface area. Okay, so here when you take this discharge, it is given here 0.6 meter cube per second. Then surface area. So here surface area you can take. So here see, in this question this length they have given, and here the width and the depth is given. So here in this question we can consider this length and width from here and calculate the area, that is 20 into 6 meter. Then you will get the SOR. Then what you have to do is, what is the percentage of the removal, that is equal to settling velocity of the given particle divided by settling velocity of the concerned size of the particle. Concerned size, that means here you are looking for the SOR. So you divide with SOR, then you get the percentage. You have to calculate first this SOR, then settling velocity of the given sample is given. So this is the settling velocity. This is 0.003 meter per second, which is given. And then they have given, then we are calculating the SOR, that is the settling velocity of the particle, that is the overflowed part, like overflow rate we are calculating from this, and then we are dividing with that. That means this SOR means settling velocity of the concerned size particle which is in the flow. So you divide with SOR, you will get the percentage of the removal. Discharge is given, and here the surface area we have to calculate the surface area. Then here you will get meters cube. Yes, 60 percentage is the right answer. Yes. 60 percentage got. Okay, so that means here it is 0.003 divided by, what is this answer is, zero point 0.6 divided by 20 into 6. Okay, yeah, 0.005 and point, I think point 0.6, right? Point 0.6, which is equal to 60 percentage. Okay, okay, then next question. Next question, average flow in a municipal wastewater. Okay, this is the same. Okay, no. So average flow in a municipal wastewater treatment plant is 5,000 meter cube per day. Determine the approximate diameter of a circular primary clarifier to remove suspended solids at average flow. Assume flow rate of 30 meter per day and a depth of 3 meter. So here we, it is given average flow is given. So average flow is given. So average flow is 5000 meter cube per day. So you convert into meter cube per second. Convert it. How do you convert? Divided by 24 hours, 30, 60 minutes, 60 second, meter cube per second, right? Then determine the approximate diameter of the, okay, so diameter we have to find out to of a circular primary clarifier to remove suspended solids at average flow. Assume overflow rate is 30 meter per day. So and then depth is 3 meters. So D is equal to 3 meter. Then assume overflow rate. So this overflow rate is given like overflow rate equal to 30 meter per day. So how do you convert into 30 meter per second? So otherwise you can keep in, okay, yeah. So okay, 30 meter per second also you can do it, divided by this 24 into 60 into 60 meter per second. Okay, now you have to calculate the diameter. First, area you can calculate. Area is equal to, um, already in the previous question, it we have calculated how Q divided by flow rate. This, so okay, so you don't need to convert. Yeah, you don't need to convert. Yes. This flow rate, overflow rate you can do, right? So here, yeah, so this you don't need to convert anyway because here it is dividing. So this is like 5000 divided by 30. So what is the value you get here? 5000 divided by 30. That is 166.67 meter square. So you calculate the area. So now it is given like circular like clarifier. So the area of a circular clarifier is area is A is equal to pi d square divided by 4. So area we have, this is the area. You don't need to convert this meter cube per day into meter cube per second or 30 meter per day to meter per second because we are calculating the area by dividing the same term. So this will get cancelled and we get the area. So put the area value here. So you get 166.67 equal to pi by 4 into d square. So calculate this d from here. What is the d? B. Yes, right. Let me also calculate. Point. Yes, 14.5 is the answer. Calculated? Any doubt? Okay, then next question. Okay, so next question is a grid chamber of dimensions, 12.5 meter into 1.2 meter into 80 meter. Depth has a depth, liquid depth has a flow of 875 meter cube per hour. Its surface loading rate is approximately equal to what? So we have to calculate the surface loading rate. So first, it what surface loading rate is? Surface loading rate we have to calculate. So first of all, Q is given, flow is given, which is 875 meter cube per hour. So then dimensions are given here. Then what you have to do is area. So area is equal to, this is length. So 12.5 into this one. So here you'll get the area length into width equal to 112.5 into 1.2. What is the value? It is like 15 meters square. You got the area. So then from here you can calculate the surface loading. What is the surface loading? How do you calculate? 58 is the answer. Q by A. 875 divided by 15. So in what you get? 875 divided by 15. You get 58.33 in meter. Sorry, it is, this is meter cube per hour, and this is area is meter square. So this meters per hour. So here, see, answer is this D, right? Huh? So here see meter cube per hour, and it is given like meter square. So it is like meter per hour. Got it? Yes. Okay. Yeah. This clear. So we'll end the questions for today. So for this, what are the doubt you people have for this class? I will take in next class. What are the things I have to explain more? So this thing you told, this one. So any other thing I have to explain next class? Anything? Real settling. Okay. Real settling and ideal settling. Okay. So actually I am working in the tertiary treatment of the wastewater. That's why I need some, research to get to know the full of these all things. Okay. So what ideal and real, right? Real settling. Okay. Then what else? What else? Two. Then anything you want to know? For the next class I will explain more deeply if anything I have to explain. This thing is needed. What is the equalization tank, how it works, more with the graphical thing. Okay, any more? Sorry. Screen. Okay, regarding the dimensions. Uh-huh. Okay, diagram. Okay, okay. Yeah, I will take this diagrams next class. Okay, enough, right? Fine, can we leave for today? Hope. Huh? Huh? I can't, either actually, mass balance. Huh. Okay. In what? In the measurement. In the measurement, right? Okay. Okay. In the reactor. Huh. Okay. 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 Yes. Okay. Okay. Yeah. Huh. Okay. Because I think in the concentration we can measure at any point. Okay. But I will take in the deep of that. Yes. Yes. That I can explain. Anything? Any more? Okay. Screening. Okay. Hmm. 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 Okay. Okay. So in the clarif. Okay. So you're seeing that how the this mean depth, what is the distance you're asking, right? Haha. Yes. So here, see, the mean depth is here. This one. So till this way it is taking out. See here, this depth. So here the depth is, see, more less depth. So only at this portion it will be high, but most of the pipes have lesser depth. That one only, right? Huh? Okay. Okay, then next class I will come with some more diagrams for proper understanding for the screens. Yes. Yes. Okay. Okay. Any more? Can we leave for this class? Okay. Thank you. Okay, we'll meet next class. Okay. Thank you. Thank you.